All right, today we're jumping into a really core concept in probability, independent events. Put simply, it's when the outcome of one thing has absolutely zero impact on the outcome of another. But how do we actually prove that with math? Well, that's what we're here to figure out.
So to get us started, just think about a standard 52-card deck. If I draw a card and I tell you, hey, this card is a spade, does that information change the odds of it also being an ace? Just take a second. What does your gut tell you? That intuition is a great place to start. So yeah, we're going to use this card question to really build up our intuition before we get into any of the formal rules. Look, intuition is great. It gets you a long way. But in statistics, you need proof. You need a formal rule. So let's look at the actual mathematical test for independence.
Okay, and here it is. This little formula is the mathematical heart of independence. It says that two events, let's call them E and F, are independent if the probability of both of them happening together, that's what PEF means, the intersection, is exactly equal to the probability of E happening multiplied by the probability of F happening.
So what's the big takeaway here? All this formula is really saying is that knowing event F happened gives you absolutely no new information about the chances of event E. The probabilities just don't influence each other.
All right, so theory's great, but let's see this thing in action. We're going to apply this rule directly to our card problem and see if our intuition was on the money.
Okay, let's get formal. We'll define our events. Event E is the card is an ace, and event F is the card is a spade. The big question we need to answer with our new rule is, are these two events independent? We're just going to walk through this step by step. First up, the probability of drawing an ace, P of E. Well, there are 4 aces, so that's 4 out of 52. Easy enough. Second, the probability of drawing a spade, P of F. There are 13 spades, so that's 13 out of 52. And third, what's the probability of both? That means drawing the ace of spades. There's only one of those, so that's 1 out of 52. Now for the final step, we just need to check if P of E times P of F equals P of EF.
And what you look at that. When we multiply them out, 4 over 52 times 13 over 52, that gives us 52 over 2,704, which, if you simplify it down, is exactly 1 over 52. And that is precisely our P of EF. They match. The condition is met, so these events are officially independent. Our gut feeling was right.
Okay, so that one seemed pretty straightforward, right? But what happens when things get a little less obvious? Let's switch gears and try a new problem with dice where our gut feelings might just lead us astray. And this is exactly why we need that formal rule, because intuition gets real tricky here. So let's walk through scenario 1. The probability of the sum being 6, P of E1, is 5 out of 36 possible rules. The probability of the first die being a 4, P of F, is 1 out of 6. If they were independent, the product would be 5 out of 216. But what's the actual probability of both happening, the sum being 6 and the first die being a 4? Well, that means you had to roll a 4 and then a 2. That's just one specific outcome out of 36. So P of E1F is 1/36. Since 1/36 is not equal to 5/216, these events are dependent. Now look at scenario 2. The probability of the sum being 7 is 6/36, or 1/6. The probability of the first die being a 4 is still 1/6. Their product is 1/36. And what's the actual chance of both? To get a sum of 7 with the first die being a 4, you have to roll a 4 and a 3. That's exactly a 1 in 36 chance. Here, the numbers match perfectly. The events are independent. I mean, this is the perfect example of why we can't always trust our gut. We need the math. Okay, now let's tackle a really common point of confusion. The difference between events being independent versus being mutually exclusive. So let me just ask you this straight up. If two events are mutually exclusive, meaning they cannot possibly happen at the same time, does that make them independent? I mean, it kind of sounds plausible, but let's dig in a little closer. You can see the difference laid out perfectly here. For independent events, they absolutely can happen together. Think about drawing the ace of spades. But for mutually exclusive events, by their very definition, the probability of them happening together is 0. It's impossible. Think about it. When you flip a coin, it can't land on both heads and tails. And here is the absolute key takeaway. If two events are mutually exclusive, they are actually extremely dependent on each other. Why? Because knowing that one of them happened tells you with 100% certainty that the other one did not happen. That's a massive amount of information, making them the total opposite of independent. Okay, now that we've got those core ideas down, let's see how independence plays out when you have sequences of events, like repeated trials of success and failure.
So here's a classic problem type that you'll see all over the place. Imagine you have some experiment. It could be shooting a free throw, a quality check on a product, and it has a probability of success that we'll just call P. Now, if you run this experiment n times, what are the odds that you get at least one success? Now, trying to calculate at least one directly is actually pretty hard. You'd have to calculate the probability of one success plus two successes all the way up to n. So we use this really clever trick. We calculate the probability of the exact opposite happening, getting 0 successes. The chance of one failure is just 1 minus p, right? And since each try is independent, the chance of n failures all in a row is just 1 minus p raised to the power of n. So the probability of getting what we actually want, at least one success, is simply 1 minus that probability of total failure.
So we've seen the math, we've gone through a few examples, but why does this actually matter? Let's take a step back and connect these ideas to the real world, because this concept is the foundation for so much of modern statistics.
The thing is, this assumption of independence is a cornerstone in so many fields. In manufacturing, you're checking if defects on an assembly line are independent events or if they point to a bigger problem. In finance, tons of models assume daily stock returns are independent, though that's a very hot debate. And of course, in medicine, it's absolutely critical for analyzing patient data in clinical trials. This assumption is everywhere.
But that brings us to a huge, crucial warning. Assuming events are independent makes the math way easier. But if you're wrong, if that assumption doesn't hold up, your entire model, your whole analysis could be completely worthless and even dangerous. You have to always verify it. And I'll leave you with this last thing to think about. The formal definition of independence means one event gives you 0 information about another. But in the world we live in, this hyper-connected, data-rich world, where it feels like everything influences everything else, it really makes you wonder, is anything ever truly, perfectly independent?